I'm so glad you found your way here. The universe beyond our small world is vast and ancient, filled with travelers that drift between the stars for billions of years. Tonight, we'll journey gently alongside one of these cosmic wanderers, a visitor from beyond our solar system, named 3I/Atlas. Welcome to Get Sleepy Science. Wherever you are right now, perhaps beneath a roof that shields you from the vast night sky, or with the gentle darkness pressing softly against your windows, allow yourself to settle into this shared moment of stillness. We'll explore 100 remarkable truths about this interstellar comet, discovered just months ago, in July of 2025. From the moment it was spotted drifting through space, 8 billion miles from the Sun, to its journey past Mars and through the inner solar system, to the mysteries it carries about the ancient galaxy it came from. If these calm stories from the cosmos help you slow down, a soft like, or share some thoughts in the comments, helping more curious minds drift this way, one sleepy soul at a time. It only takes a moment, but it means the universe to us. We'd be grateful. For now, just let your shoulders soften, let your breathing fall into its own rhythm. Imagine yourself drifting in a space of gentle curiosity, where facts become stories and stories become dreams. There's nothing you need to do, nowhere you need to be. Close your eyes and take a deep breath. You're lying in a small spacecraft, drifting gently through the endless night sky, moving without boundaries, without destination, only the light of distant stars and absolute silence. Let go of all limits. Let your mind drift through the vast empty space between worlds, where ancient travelers pass through the darkness. Astronomers discovered something unusual on July 1st, 2025. A faint dot of light moving through space, captured by the Atlas telescope in Chile, appeared different from anything nearby. When scientists calculated its path, they realized this object wasn't from our solar system at all. It was traveling too fast, moving on a trajectory that could only mean one thing. This visitor had come from interstellar space, from somewhere beyond the influence of our Sunday. They named it 3I/Atlas, the third confirmed interstellar object ever observed by humanity. In the vast cosmic ocean, we had spotted another traveler passing through our small corner of the galaxy. This scientific impression suggests how rare and precious each of these encounters truly is. 3I/Atlas is moving at a breathtaking speed. When it entered our solar system, it was traveling at approximately 36 miles per second relative to the Sunday. That's roughly 130,000 miles per hour, moving at speeds beyond what our spacecraft achieve. This speed is what scientists call hyperbolic excess velocity, the extra speed an object has beyond what gravity alone would give it. By comparison, the fastest human-made object, the Parker Solar Probe, reaches about 430,000 miles per hour at its closest approach to the Sunday. The comet's natural velocity reveals it has been wandering through the galaxy for an immense amount of time, accumulating speed from ancient gravitational encounters we can only imagine. The discovery required fortunate timing. 3I/Atlas was passing in front of the Milky Way's galactic center during late June 2025, moving through dense star fields where it blended among countless stars, like trying to find a single dim firefly against a field of streetlights. Amateur astronomers later found images from early June that showed the comet was already there, unnoticed. Only when it emerged from this cosmic camouflage did the Atlas survey finally catch it on July 1st. Sometimes the most important discoveries require both sophisticated technology and a bit of cosmic timing. We see what we see when the universe allows us to see it. This visitor carries the designation 3I/Atlas, which tells us several things. The I stands for interstellar, confirming it came from beyond our solar system. The 3 means it's the third such object we've confirmed. The first was Oumuamua, discovered in 2017. The second was Comet 2I/Borisov, found in 2019. And now 3I/Atlas joins this rare collection. Atlas refers to the Asteroid Terrestrial Impact Last Alert System, the network of telescopes that found it. In just under a decade, humanity has identified 3 confirmed visitors from other star systems. Each one teaches us something new about the galaxy beyond our home. It's a reminder that space, while vast and empty, is also full of wanderers. When 3I/Atlas was first spotted, scientists weren't sure what it was. The initial images showed only a faint point of light, dim and unremarkable. It could have been an asteroid, a comet, or even a piece of space debris. But as astronomers continued observing it over the following days and weeks, something changed. The object began showing signs of activity. A faint glow appeared around it, a halo of gas and dust that astronomers call a coma. Then came the first hints of a tail, material streaming away from the object as it warmed. These are the signatures of a comet, an icy body releasing frozen gases as it approaches the Sunday. 3I/Atlas revealed itself slowly, like a traveler removing layers of protective clothing upon arriving somewhere warmer. The comet's orbit is remarkably unusual. Scientists describe orbits using a number called eccentricity. A perfect circle has an eccentricity of 0. Earth's slightly oval orbit has an eccentricity of about 0.017. Objects bound to the Sun, like planets and most comets, have eccentricities less than 1, but objects from interstellar space have eccentricities greater than 1, indicating they're not trapped by the Sun's gravity. 3I/Atlas has an orbital eccentricity of 6.139. This is extraordinarily high, the highest ever recorded for any object in our solar system. Its path is so open, so far from circular, that it appears almost straight as it cuts through our cosmic neighborhood. It arrived, and it will leave, following a path that barely curves. How big is 3I/Atlas? Observations from the Hubble Space Telescope through August 2025 helped astronomers estimate the nucleus size. The upper limit appears to be about 3.5 miles across, though the nucleus could be as small as 1,400 feet. The exact size remains uncertain, because the bright coma surrounding it makes precise measurements challenging. Even with our most powerful telescopes, some cosmic measurements require patience and many observations. What we do know is that 3I/Atlas is considerably larger than the previous interstellar visitor, 2I/Borisov, which was less than half a mile across. 3I/Atlas carries a kind of cosmic identification card in its motion. When scientists calculated where it had been in the distant past, tracing its path backward through the galaxy, they discovered something fascinating. The comet likely originated from the Milky Way's thick disk, a region of the galaxy populated by older, ancient stars. These stars formed billions of years ago, when the galaxy was younger and the universe looked very different. By analyzing how far 3I/Atlas rises above and below the galactic plane as it travels, researchers estimate the comet is approximately 4.6 to 9.6 billion years old. That means this traveler is older than our entire solar system, which formed about 4.6 billion years ago. It's an elder wanderer, carrying traces of the early galaxy within its frozen structure. The comet's trajectory brought it surprisingly close to Mars. On October 3, 2025, 3I/Atlas passed just 19 million miles from the red planet. In astronomical terms, This is quite close, about 1/5 the distance between Earth and the Sunday. Multiple spacecraft orbiting Mars had the opportunity to observe this interstellar visitor from relatively nearby. NASA's Mars Reconnaissance Orbiter, the MAVEN spacecraft, and China's Tianwen-1 orbiter all captured images. Even the Perseverance rover on Mars's surface managed to photograph a faint smudge of light in the Martian sky. These observations from multiple angles helped scientists understand the comet's three-dimensional structure and refine their calculations of its path. Space missions designed for other purposes became unexpected witnesses to a rare cosmic event. Earth is nowhere near 3I/Atlas's path. The closest approach to our planet will be on December 19th, 2025, at approximately 170 million miles, nearly twice the distance between Earth and the Sunday. The comet poses absolutely no threat to Earth. We can observe in peace, gathering knowledge from a safe distance. 3I/Atlas reached its closest point to the Sun on October 29th and 30th, 2025. This moment, called perihelion, occurred at a distance of about 1.4 astronomical units, or roughly 130 million miles from our star. That placed the comet just inside the orbit of Mars, receiving more solar heat than it had experienced in billions of years of drifting through the cold of interstellar space. As it approached perihelion, the comet began heating up, its frozen gases warming and turning directly from ice to vapor without becoming liquid first. This process, called sublimation, caused the comet to become more active, releasing more material and growing brighter. For a brief window of time, this ancient traveler was illuminated by our sun's warmth. The comet's composition reveals something interesting about its distant origin. Observations using spectroscopy, which analyzes the light coming from the comet, detected several specific chemicals. Scientists found water vapor, carbon dioxide, carbon monoxide, and hydrogen cyanide being released as the comet warmed. There were also traces of carbonyl sulfide and water ice particles in the coma surrounding the nucleus. Interestingly, 3I/Atlas appears to be releasing more carbon dioxide than water, which is somewhat unusual compared to many comets from our own solar system. It also shows higher nickel content relative to iron. These chemical differences suggest the comet formed in conditions slightly different from the environment where our solar system's comets were born. Each interstellar visitor carries a chemical signature from its birthplace. The speed of 3I/Atlas changed predictably as it approached and then moved away from the Sunday. When discovered in early July, it was traveling at about 137,000 miles per hour. As the Sun's gravity pulled it inward, the comet accelerated, reaching approximately 155,000 miles per hour at perihelion in late October. Now, as it moves away from the Sun, it's gradually slowing down again, still pulled back by our star's gravitational influence. Eventually, when it escapes far enough from the Sun's grip, it will return to its original interstellar velocity of about 36 miles per second. This is how gravity works. Objects speed up when falling toward a massive body and slow down when climbing away from it, following the elegant mathematics of orbital motion. Only 3 confirmed interstellar objects have ever been observed passing through our solar system. The first, Oumuamua, was discovered on October 19, 2017. It had an elongated, cigar-like shape and showed no signs of cometary activity, behaving more like a rocky asteroid. The second, Comet 2I/Borisov, was spotted on August 30, 2019 by amateur astronomer Gennady Borisov using his own custom-built telescope. Unlike Oumuamua, Borisov was clearly a comet with a visible tail and appeared quite similar to comets from our own solar system. Now 3I/Atlas represents the third confirmed visitor, combining elements of both previous objects. It's clearly a comet, but with some unusual properties that set it apart. 3 visitors in less than 8 years suggests these interstellar travelers may pass through more frequently than we once thought. The discovery of interstellar objects is changing how we think about the galaxy. Before 2017, we had never definitively observed anything from beyond our solar system passing nearby. Astronomers predicted such objects should exist, ejected from distant planetary systems during their chaotic formation billions of years ago, wandering the galaxy ever since. But prediction and observation are different things. Finding Oumuamua, then Borisov, and now 3I/Atlas confirms that space between the stars isn't completely empty. There are travelers out there, refugees from ancient systems, carrying with them frozen samples from other worlds. Each discovery provides a glimpse into planetary formation processes happening around distant stars we may never visit. In a personal reflection, it feels like receiving messages in bottles thrown into a cosmic ocean long ago. The Atlas system that discovered this comet was actually designed for a different purpose. Atlas, which stands for Asteroid Terrestrial Impact Last Alert System, is a network of telescopes funded by NASA to search for asteroids that might potentially impact Earth. 4 telescopes, located in Hawaii, Chile, and South Africa, scan the sky every night, looking for moving objects. When something new appears, the system automatically alerts astronomers. Most of what Atlas finds are asteroids and comets from our solar system. And sometimes, like on July 1st, 2025, it reveals something from much farther away, a visitor from between the stars. Technology built for one purpose often reveals unexpected wonders. 3I/Atlas will eventually leave our solar system and return to interstellar space. After passing behind the Sun in late October, it's now traveling outward, gradually escaping the Sun's gravitational influence. It will pass relatively near Jupiter on March 16th, 2026, at a distance of about 33 million miles. Jupiter's immense gravity will slightly alter the comet's path, giving it a tiny gravitational boost, but won't capture it. The comet will continue onward, moving faster and faster until it crosses the boundary where the Sun's influence fades into the background. Then it will resume its journey through the galaxy, drifting through the darkness between stars for millions or billions more years, until perhaps, impossibly far in the future, it encounters another star system. We had a brief window to observe it, and then it will be gone. Scientists used multiple space missions to observe 3I/Atlas from different vantage points. Besides the Mars orbiters and rovers, NASA's Hubble Space Telescope captured detailed images in July and August, revealing the comet's teardrop-shaped dust cocoon. The James Webb Space Telescope observed it in late August, using infrared instruments to analyze the chemicals in its coma. NASA's Psyche spacecraft, on its way to explore a metal-rich asteroid, took images in early September when it was about 33 million miles from the comet. The Lucy spacecraft, heading to study asteroids near Jupiter, photographed 3I/Atlas in mid-September from 240 million miles away. Even the SOHO and Stereo solar observatories captured the comet during its closest approach to the Sunday. This coordinated effort represents one of the most comprehensively observed comets in history. The comet showed interesting variations. As it approached the Sunday, it brightened more quickly than typical comets from our own solar system's Oort cloud, and appeared to shift toward a bluer hue at times, rather than the reddish color most comets display. Some observers noted what appeared to be multiple tails or jets emanating from different parts of the nucleus. suggesting particularly active regions on its surface, where material was being released more vigorously. These jets created a complex, fan-like structure, visible in photographs taken in early November. Such features aren't unique to interstellar comets. Many comets showed jets and active regions, but they reminded scientists that each comet is an individual, with its own particular structure and behavior shaped by billions of years of history. The name comet comes from the ancient Greek word kometes, meaning long-haired, referring to the streaming tails these objects display as they approach the sunday. Humans have observed comets for thousands of years, often viewing them with superstition and fear, interpreting them as omens of disaster. It wasn't until the 16th and 17th centuries that astronomers began understanding comets as natural objects orbiting the sunday. Edmund Halley, in 1705, was the first to realize that some comets return periodically, predicting the return of what we now call Halley's Comet. Today, we know comets are icy remnants from the formation of our solar system, frozen time capsules carrying pristine material from 4.6 billion years ago. And now we're learning that some comets come from even farther away, carrying secrets from other stars. The coma surrounding 3I/Atlas, that glowing cloud of gas and dust, grew quite large as the comet approached the sunday. By mid-September 2025, observations showed the coma extended about 112,000 miles across, roughly 14 times wider than Earth. This enormous atmosphere forms when sunlight warms the comet's surface, causing frozen gases to sublimate and carry dust particles into space. The material spreads out, creating a huge but incredibly thin cloud that scatters sunlight, making the comet visible. Despite its size, the coma contains very little actual mass, perhaps equivalent to a small iceberg's worth of material, spread across a volume larger than many planets. It's mostly empty space with suspended particles, delicate and beautiful in its fragility. Scientists were particularly interested in detecting hydrogen cyanide in the comet's coma. This molecule, abbreviated HCN, is important because it's considered a prebiotic chemical, a building block that can lead to more complex organic molecules necessary for life. The James Clerk Maxwell telescope detected hydrogen cyanide from 3I/Atlas in early September. On September 7th, the production rate was approximately 1.5 times 10 to the 25th power molecules per second. By September 14th, this had tripled to about 4.5 times 10 to the 25th power molecules per second, equivalent to roughly 4.4 pounds per second. Finding such molecules in an interstellar comet suggests the chemistry that supports life might be common throughout the galaxy. The same basic ingredients appear to form in many different environments, scattered among the stars. It's a scientific observation that hints at life's potential universality. The comet's trajectory alignment with our solar system's planetary plane was somewhat surprising. Most comets from our own Oort cloud arrive from random directions, with orbital planes tilted at all angles relative to the ecliptic, the flat disk where planets orbit. But 3I/Atlas's path is inclined only about 5 degrees from the ecliptic, moving in a retrograde direction at about 175 degrees. This near alignment means the comet passed relatively close to several planets' orbits, making it easier to observe. Some researchers noted this alignment is statistically unusual, though not impossible. It might simply be cosmic coincidence, or it could suggest something about how objects are ejected from distant planetary systems. Space holds many patterns we don't yet fully understand, and each new visitor provides another data point. Temperature plays a crucial role in a comet's behavior. When 3I/Atlas was discovered in early July, It was about 2.8 billion miles from the Sun, beyond Jupiter's orbit, where sunlight is weak and temperatures hover around -230 degrees Fahrenheit. At that distance, most water ice remains frozen solid, but carbon dioxide and carbon monoxide ices can begin sublimating even at those temperatures, which is why the comet showed early activity. As it moved inward toward perihelion, temperatures on the sunlit side gradually increased. Near its closest approach to the Sun in late October, surface temperatures could have reached several hundred degrees Fahrenheit in direct sunlight. This heating drove the comet's increased activity, releasing more material and creating the multiple tails observed. Temperature is the sculptor of cometary form. Amateur astronomers around the world contributed to observations of 3I/Atlas. People with backyard telescopes in the 4 to 8 inch range were able to detect the comet in November 2025, when it brightened to around 10th or 11th magnitude. One astronomer in Cumbria, England, used a smart telescope called a C-Star S50 to capture images on November 16th from the middle of a town, despite light pollution and the moon's interference. This successful observation demonstrated that the comet had become accessible to smaller instruments, allowing dedicated amateurs to see and photograph an object from another star system. In the tradition of astronomy, professional and amateur observers work together, each contributing pieces to our understanding. The universe reveals itself to anyone patient enough to look carefully into the darkness. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star billions of years ago. The spacecraft we build, the telescopes we aim at the sky, all made from the material of the universe, returning to the universe to study itself. Feel yourself carrying the trace of ancient stars in every cell. 3I/Atlas has been traveling for perhaps 9 billion years. You and I, we're made of matter nearly as old. We are all cosmic travelers, flying on a small planet through a galaxy full of wanderers. Now we continue. The Milky Way's thick disk, where 3I/Atlas likely originated, is an older region of our galaxy. Unlike the thin disk where our Sun resides, where active star formation continues, the thick disk is populated mainly by ancient stars formed 7 to 12 billion years ago. These stars have orbits that carry them farther above and below the galactic plane, creating a thicker band. The stars tend to have lower metallicity, meaning they contain fewer heavy elements than younger stars like our Sunday. When 3I/Atlas formed around one of these ancient stars, the universe was younger, galaxies looked different, and the chemical composition of space was not quite what it is today. This comet is a messenger from that earlier era. Comparing 3I/Atlas to the previous interstellar visitors reveals interesting differences. Oumuamua was small, estimated at only about 330 feet long, and showed no cometary activity whatsoever, appearing more like a tumbling asteroid, or possibly something even stranger. 2I/Borisov was clearly a comet, but relatively small, with a nucleus about 1,300 to 4,900 feet across, and behaved very much like comets from our solar system. 3I/Atlas is substantially larger than both, possibly miles across, shows strong cometary activity, but also displays some unusual characteristics, like its rapid brightening and color changes. Each of these three visitors is different, suggesting great diversity among objects drifting between the stars. The speed at which 3I/Atlas entered our solar system provides clues about its journey. An object's velocity in interstellar space depends on the gravitational history of its travel. Encounters with massive objects like stars or molecular clouds can speed objects up or slow them down over millions of years. The fact that 3I I/Atlas was moving at 36 miles per second suggests it experienced relatively few dramatic gravitational interactions during its long journey, or perhaps that those interactions balanced out over time. Objects ejected from planetary systems typically start with speeds of a few miles per second. Over billions of years, galactic dynamics can accelerate them. The comet's current speed is written into its motion, a record of billions of years of gravitational influences we can only partially reconstruct. When scientists integrate 3I/Atlas's trajectory backward through time, they can estimate where it has been in the galaxy. These calculations show the comet's path, rising and falling relative to the galactic plane, oscillating above and below the Milky Way's mid-disk over millions of years. The maximum height it reached, above or below the plane, about 1,000 to 2,000 light-years, corresponds to the typical scale height of the thick disk stellar population. This mathematical tracing backward through gravitational fields is how astronomers connect individual objects to broader galactic populations. It's detective work on a cosmic scale, using present motion to infer ancient origins. The universe keeps records in the form of trajectories. The dust tail of 3I/Atlas tells its own story. When sunlight strikes dust particles released from the comet, radiation pressure, the physical push of light itself, drives these particles away from the sunday. Smaller particles are pushed harder, larger ones less so, causing the tail to spread slightly. The tail always points generally away from the sun, regardless of the comet's direction of motion. Photographs from mid-September showed the dust tail extending about 62,000 miles, creating a graceful streamer in space. This tail is made of tiny particles, mostly silicate minerals and organic compounds that were locked in the comet's ice for billions of years. Now, warmed by an alien sun, they drift free, spreading into space where they'll eventually disperse and perhaps someday become part of another world. Hydrogen atoms detected around 3I/Atlas by the MAVEN spacecraft's ultraviolet spectrograph revealed the comet's water content. When water molecules in the coma are broken apart by sunlight, a process called photodissociation, they split into hydrogen and oxygen. The hydrogen, being very light, forms an enormous cloud around the comet, much larger than the visible coma. MAVEN's observations in late September 2025 detected this hydrogen envelope, distinguishing it from hydrogen naturally present in interplanetary space and hydrogen in Mars's upper atmosphere. By measuring the hydrogen, scientists could estimate how much water the comet was releasing. These measurements help determine the comet's composition and activity level, telling us about conditions in the distant system where it formed. The concept of panspermia, the idea that life's building blocks might spread between star systems on comets and asteroids, gained renewed interest with interstellar objects. If comets like 3I/Atlas carry organic molecules and prebiotic chemicals, and if such objects regularly travel between stars, then the ingredients for life might be distributed throughout the galaxy. A comet ejected from one planetary system could theoretically deliver complex organic molecules to another system millions or billions of years later. While this doesn't mean life itself travels this way, it suggests that the chemistry leading to life might not need to start from scratch in each system. The galaxy might be sharing recipes for life, written in frozen molecules carried by wandering comets. It's a possibility that makes the universe feel more connected. Observing 3I/Atlas required careful timing. The comet was visible from Earth through telescopes from July through late September, before it passed too close to the sun's glare to observe. During late October and much of November, it was lost in solar conjunction, hidden behind or very near the sun in our sky. By early December, it emerged on the other side, visible again in the pre-dawn sky. This reappearance gave astronomers another opportunity to study it after perihelion, seeing how the close solar encounter might have changed it. Some comets break apart or dramatically alter after perihelion. Others fade quickly as their most volatile materials are depleted. Each reappearance after perihelion provides new information about a comet's structure and durability. The Vera C. Rubin Observatory, which began operations recently, is expected to dramatically increase the detection rate of interstellar objects. This telescope, located in Chile, can survey the entire visible sky every few nights, detecting faint, moving objects that other surveys might miss. Scientists predict it could discover an interstellar object every few months rather than every few years. If this prediction proves true, we'll soon have a much larger sample of these travelers to study, allowing us to understand their properties statistically rather than as individual curiosities. The next decade might be remembered as the era when interstellar objects transformed from rare novelties to a recognized population, opening a new window into the galaxy around us. The ion tail of 3 I/Atlas, distinct from the dust tail, is formed by a different process. When gases sublimate from the comet, ultraviolet light from the sun ionizes some of these molecules, stripping away electrons and creating charged particles. The solar wind, a stream of charged particles flowing from the sun, then sweeps these ions directly away from the sun at high speed. Ion tails are typically bluish in color from carbon monoxide and other molecules, and they point precisely away from the sun, sometimes appearing straight. During 3 I/Atlas's perihelion passage, spacecraft like Europa, Clipper, and Hera were predicted to pass through the comet's ion tail, providing rare opportunities to directly sample an interstellar comet's ionized gases. These encounters could reveal the comet's composition with unusual precision. Light takes time to travel, and this affects how we observe comets. When we looked at 3 I/Atlas in July 2025, we were seeing it as it was about 38 minutes earlier, the time light took to travel from the comet to Earth at that distance. When Mars orbiters photographed it in October, they saw it as it was just minutes earlier due to their closer proximity. This light travel time seems short, but it reminds us that all astronomical observations are views into the past. The starlight visible tonight left those stars years, centuries, or millennia ago. We observe the universe not as it is, but as it was, watching history unfold at the speed of light. Even nearby cosmic events are historical documents by the time we see them. Scientists have estimated the comet's mass based on its approximate size and assumed density. If the nucleus is several miles across, with a typical cometary density around half that of water ice, the mass would be in the range of tens of billions of tons. These are rough estimates, as precise measurements of both size and density remain challenging. Despite this mass, the comet is tiny compared to planets or even large moons. It's a reminder that even impressive cosmic objects are small against the scale of planetary systems and stars. The process of cometary sublimation is delicate and complex. As sunlight warms a comet's surface, different ices sublimate at different temperatures. Carbon dioxide begins sublimating at temperatures around -190 degrees Fahrenheit. Carbon monoxide sublimates at even lower temperatures. Water ice, the most abundant ice in many comets, doesn't sublimate substantially until temperatures rise above -100 degrees Fahrenheit. This creates a layering effect, where different materials release at different distances from the sunday. Early observations of 3 I/Atlas showed carbon dioxide activity when the comet was still quite far from the sun, suggesting a carbon dioxide-rich composition. As it moved closer, water release increased. The sequence of which gases appear tells scientists about the comet's structure and composition. Some researchers proposed sending a spacecraft to intercept a future interstellar object. The European Space Agency's Comet Interceptor mission is designed to wait in space at a stable gravitational point, ready to be deployed toward a newly discovered long-period comet or potentially an interstellar visitor. When an appropriate target is identified, the spacecraft would quickly maneuver to intercept it, capturing close-up images and data that Earth-based telescopes cannot obtain. While 3I/Atlas arrived too soon for Comet Interceptor to reach it, future interstellar objects might be accessible. Such missions would transform our understanding, providing direct measurements of these travelers from other stars. It's the difference between watching a ship pass on the horizon and actually going aboard to explore. The discovery of interstellar objects challenges us to rethink what local means in astronomy. For most of history, astronomy was the study of distant, unreachable objects, stars and galaxies forever beyond our reach. Even the solar system seemed vast, but interstellar objects occupy a middle ground. They're not from here, yet they pass through our neighborhood. They're not bound to our sun, yet we can observe them with the same telescopes we use to study local comets. They represent the first time humanity has directly observed matter from other star systems within our own cosmic backyard. In a philosophical sense, they blur the boundary between here and there, between our system and the galaxy beyond. The cosmos comes to visit us. You're still here, still awake, still drifting with us through these stories from the stars. Take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I and everyone listening in the quiet, dark, floating through facts like ancient comets drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. Comets like 3I/Atlas are essentially dirty snowballs, mixtures of ice, dust, and rock, left over from the formation of planetary systems. When a star forms from a collapsing cloud of gas and dust, the leftover material forms a disk around the young star. Planets form in this disk, but not all material becomes part of planets. Much of it remains as smaller bodies, asteroids in the inner regions where temperatures are high, and comets in the outer, colder regions where ice can survive. Some comets get ejected from their home systems during gravitational interactions, escaping to wander the galaxy. 3I/Atlas is one such refugee, expelled from its birth system billions of years ago and traveling ever since. The color of a comet can reveal information about its composition and structure. Sunlight reflecting off a comet typically gives it a slightly reddish color due to organic compounds in the dust. But 3I/Atlas showed unusual blue coloration at times during its closest approach to the Sunday. This bluish tint might come from enhanced carbon monoxide in the ion tail, or from the way sunlight scattered through the comet's particular mix of gases and dust. Some observers noted the color seemed to change over time, perhaps as different regions of the nucleus became active or as the viewing geometry shifted. Colors in space are subtle, often requiring careful measurement to detect, but they carry information about chemistry that shape and brightness alone cannot provide. The concept of escape velocity helps explain how objects become interstellar. Every massive body, whether a planet, star, or galaxy, has an escape velocity, the minimum speed needed to permanently leave its gravitational influence. Earth's escape velocity is about 7 miles per second. The Sun's escape velocity from Earth's distance is about 26 miles per second. For a comet to become interstellar, it must somehow be accelerated beyond its parent star's escape velocity. This typically happens during close encounters with massive planets like Jupiter, where gravitational slingshots can boost objects to extreme speeds. Once traveling faster than escape velocity, the object leaves its home system forever, becoming an interstellar wanderer. The rotation of 3I/Atlas affects how evenly it releases gas and dust. Most comets rotate, spinning on an axis as they travel through space. When the Sun illuminates different parts of a rotating nucleus, sublimation occurs unevenly, creating jets from the areas currently in sunlight. If a comet spins rapidly, these jets can appear as a spiral pattern as material streams outward, while the nucleus rotates beneath. The multiple tails and complex structure observed in 3I/Atlas during November might result from such rotational effects. Each comet has its own rotation rate and axis tilt, creating unique patterns of activity. It's a reminder that these are tumbling, irregular objects, not smooth spheres. Scientists distinguish between asteroids and comets based on activity rather than just composition. An asteroid is typically an inactive, rocky, or metallic body, while a comet shows activity, releasing gas and dust when warmed. But this distinction can blur. Some asteroids might be dormant comets with crusted surfaces that no longer release gases. Some comets might be mainly rock, with only a thin coating of ice. When 3I/Atlas was first discovered, it took several days of observation to determine it was a comet. The initial faint appearance suggested an asteroid. Only as the coma developed did its cometary nature become clear. These categories help us organize observations, but nature doesn't always fit neatly into our classifications. The gravitational influence of planets can slightly alter a comet's path through small perturbations. As 3I/Atlas passed Mars, the red planet's gravity gently tugged on it, changing its trajectory by a tiny amount. Jupiter's larger mass will create a more noticeable deflection when the comet passes in March 2026. These gravitational nudges are small compared to the comet's overall motion, but they accumulate. An object passing through a planetary system experiences many small pulls from all the planets it passes, each one slightly altering its path. By the time 3I/Atlas leaves our solar system, its trajectory will be minutely different than it would have been had it passed through empty space. The solar system leaves its mark on travelers passing through. The observation of any interstellar object is time-sensitive. These visitors pass through our solar system relatively quickly, visible for only months before disappearing back into the depths of space. Oumuamua was observable for only about 80 days in late 2017 before it faded from view. 2I/Borisov remained visible for several months in late 2019 and early 2020. 3I/Atlas, discovered in July 2025, will likely be observable with large telescopes into spring of 2026 before becoming too faint to detect. After that, it will continue its journey, but we'll have lost our window. This temporary visibility creates urgency among astronomers to gather as much data as possible while these rare visitors are within reach. The surface of a cometary nucleus is probably very dark. Although comets appear bright due to their glowing coma and tail, the actual solid nucleus reflects very little sunlight, typically only 3 to 5%, making it darker than coal. This low reflectivity, called albedo, comes from the organic compounds and carbon-rich dust mixed with the ice. It's similar to the dark surface of carbonaceous asteroids. If you could stand on the surface of 3I/Atlas's nucleus, you'd see a dark, dusty landscape, porous and fragile, with jets of gas and dust erupting from active areas as sunlight warmed the ground beneath your feet. Of course, you couldn't actually stand there. The gravity is far too weak, and the released gases would envelop you. But it's a vivid mental image of these ancient, dark snowballs. The concept of stellar populations helps us understand where 3I/Atlas came from. The Milky Way contains stars of different ages and compositions, organized into populations. Population 1 includes young, metal-rich stars like our Sun, found primarily in the thin disk. Population 2 consists of older, metal-poor stars in the thick disk, halo, and globular clusters. When researchers traced 3I/Atlas back through the galaxy and estimated its age at billions of years, they associated it with the older, thick disk population. This tells us the comet formed around an ancient star, possibly when the galaxy looked quite different. Understanding these populations helps us place interstellar visitors in the broader context of galactic evolution. Every observation of 3I/Atlas required accounting for Earth's motion. Our planet orbits the Sun at about 67,000 miles per hour, simultaneously rotating on its axis at over 1,000 miles per hour at the equator. When astronomers calculate a comet's position and trajectory, they must subtract Earth's own motion to determine the comet's true path through space. This process, converting from Earth-centered coordinates to Sun-centered coordinates, is fundamental to astronomy. It's a reminder that we observe the universe from a moving platform, spinning and orbiting through space. Our viewpoint is never still, adding complexity to the already challenging task of tracking distant, fast-moving objects. Let's pause here in the middle of our journey. Close your eyes. Breathe slowly. Think about time for a moment. 3I/Atlas has existed for perhaps 9 billion years, traveling through space, alone, silent. You and I exist for decades, maybe a century, if we're fortunate. But right now, in this second, our brief existences overlap with this ancient traveler's story. Your time is yours, a separate stream that only you are living, while the vast universe continues to spin, expand, change. This second, this breath you're taking now, is yours, uniquely. The comet knows nothing of us, yet we know of it. Consciousness creates connection across impossible distances and times. Let each breath guide you to realize time is relative, but this moment is real, and we continue drifting. The Oort cloud, a vast spherical shell of icy bodies surrounding our solar system, is where most of our local comets originate. It extends from about 2,000 to 100,000 astronomical units from the Sun, far beyond the planets. Gravitational perturbations from passing stars occasionally nudge Oort cloud comets inward, where they can become visible. But 3I/Atlas didn't come from there. It came from an equivalent structure around another star, light years away. Every star with planets probably has its own Oort cloud, its own reservoir of icy remnants. Occasionally, these clouds lose members, sending them wandering. The galaxy is full of such exiled objects, traveling between the stars. 3I/Atlas is one of them, passing through our space after unimaginable time. The night sky appears static, but everything in it is moving. Stars orbit the galactic center. Planets orbit their stars. Moons orbit their planets. Even our Sun, carrying all its planets, orbits the Milky Way center once every 230 million years or so. Against this universal motion, 3I/Atlas cuts a path determined by its billion-year history. Its trajectory through our solar system is just a brief, straight line in a journey that spans the galaxy. We happen to notice it during the few months it was nearby. For most of its existence, it travels unseen through the dark between stars, where there's nothing to illuminate it, no watchers to observe. We caught a glimpse, and that glimpse teaches us. Dust released from comets doesn't disappear. It spreads through space, gradually dispersed by radiation pressure and gravitational forces. Over millions of years, cometary dust from objects like 3 I/Atlas becomes part of the interstellar medium, the thin gas and dust between stars. Some of this material eventually gets incorporated into new star systems, forming from collapsing molecular clouds. In this way, comets help distribute material throughout the galaxy, mixing the chemical products of stellar evolution. Our own solar system's comets contributed dust that may have rained down on early Earth. Now 3I/Atlas's dust, born in another system, will add its contribution to the galactic mix. Material circulates through the cosmos, never created or destroyed, only transformed. The brightening of 3I/Atlas near perihelion occurred faster than typical comets. Comets typically brighten in predictable ways as they approach the Sun, following mathematical formulas based on distance and activity level. But 3I/Atlas brightened faster than these models suggested, indicating either a more active surface than anticipated or perhaps structural changes as warming reached deeper into the nucleus. Sudden brightening can occur when fresh, volatile rich ice becomes exposed, or when protective dust layers crack and release trapped gases. Each comet's brightness curve tells a story about its structure and composition. Faster brightening means the comet held variations not visible from its outward appearance. Detecting interstellar objects requires automated survey systems. Human observers can't monitor the entire sky continuously, but telescopes linked to computer systems can. These surveys take multiple images of the same areas of sky nights apart, comparing them to find objects that have moved. Software identifies candidates, which are then checked by human astronomers. The Atlas system processes enormous amounts of data every night, finding hundreds of moving objects. Most are known asteroids, some are newly discovered asteroids or comets from our solar system. Rarely, very rarely, one turns out to be from interstellar space. These automated sentinels work tirelessly, expanding our knowledge while we sleep. The term hyperbolic trajectory describes paths that never close into an orbit. Imagine throwing a ball upward. If thrown gently, it falls back down, following a closed path. Throw it harder, and it goes higher before falling. At a specific speed, escape velocity, it would never return, following an open parabolic path. Throw it faster still, and its path becomes hyperbolic, opening even wider. 3I/Atlas's trajectory is extremely hyperbolic, with an eccentricity over 6, meaning its path barely curves as it passes through our solar system. It arrived from one direction, swung past the Sun, and will depart in a completely different direction, never slowing down enough to be captured. Hyperbolic objects are just visiting, true travelers rather than residents. The space between stars seems empty, but it holds a thin mix of gas and dust called the interstellar medium. Its density is extraordinarily low, typically less than 1 atom per cubic centimeter. Yet over vast distances, this adds up. Temperatures hover just a few degrees above absolute zero, around -450 degrees Fahrenheit. For 3I/Atlas, this profound cold preserved its ancient ice for billions of years, keeping it frozen and unchanged since formation. Cosmic rays, high-energy particles permeating space, can chemically alter surface ice over time. Only now, warmed by our Sun, do these ancient ices begin to release molecules frozen since before Earth existed. In a sense, studying 3I/Atlas is like opening a time capsule from the early galaxy. Not all interstellar objects would be visible to us. Small objects, perhaps only yards across, would be too faint to detect with current technology unless they passed extremely close to Earth. We've likely been visited by many small interstellar travelers that went completely unnoticed. Statistical estimates suggest that at any given time, there might be several interstellar objects within the orbit of Neptune, most too small or distant to detect. We see only the tip of a vast iceberg, the largest and closest visitors. As telescope technology improves and automated surveys become more sensitive, we'll discover smaller and more distant interstellar travelers. The population we currently observe is biased toward the brightest and nearest. The light from 3I/Atlas tells us about its size indirectly. By measuring how much sunlight the comet reflects and knowing how far it is from both the Sun and Earth, scientists can calculate an approximate size for the nucleus. Brighter objects are typically larger, though their reflectivity matters too. A small, highly reflective object can appear as bright as a larger, dark object. Combining brightness measurements with spectroscopic data about composition helps refine size estimates. For 3I/Atlas, measurements suggest a nucleus several miles across, though the exact size remains somewhat uncertain. These calculations rely on assumptions about the comet's shape and surface properties, introducing unavoidable uncertainty into our estimates. Ancient cultures saw comets as supernatural omens. Chinese astronomers recorded comets for over 2,000 years, viewing them as celestial signs related to earthly events. European medieval observers often interpreted comets as warnings of disaster, plague, or political change. The appearance of a bright comet might be linked to the death of a king or the outcome of a war. We now understand these associations were coincidental. Comets are natural objects following predictable paths, having nothing to do with human affairs. Yet there's something poetic in the old belief that heavens and earth are connected. While comets don't predict our futures, they do connect us to the broader universe, messengers from deep space reminding us of our place in the cosmos. The solar wind, a stream of charged particles constantly flowing from the sun, interacts with comets in fascinating ways. As solar wind encounters a comet's coma, it can't pass through the dense gas cloud easily. Instead, it flows around the obstacle, creating a bow shock similar to how water flows around a rock in a stream. This interaction forms a magnetosphere around the comet, even though the comet itself has no magnetic field. The solar wind also sweeps ions from the coma away from the sun, forming the ion tail. These processes were predicted by theory before being observed. 3I/Atlas, despite coming from another star, responds to our solar wind just as local comets do. Physics works the same throughout the universe. Every comet loses mass. As it passes near the Sunday sublimation, carries material away that can never return. For objects like 3I/Atlas, making a single pass through our solar system, this mass loss is permanent. By the time it leaves, it will be noticeably smaller than when it arrived, having lost perhaps millions or billions of tons of ice and dust over many perihelion passages, which would happen for comets orbiting the Sun. This mass loss eventually destroys the comet. Some break apart completely. Others develop thick crusts of non-volatile material that seals in remaining ice, becoming dormant. But 3I/Atlas will never return. Its single passage here represents a unique moment in its multi-billion-year existence, a brief warming after eons of cold before it returns to the frozen dark. The study of comets has deep historical roots. In 1705, Edmund Halley analyzed historical comet sightings and realized that comets seen in 1531, 1607, and 1682 followed similar paths. He proposed they were the same object, returning every 76 years, predicting its return in 1758. Halley didn't live to see his prediction confirmed, but the comet returned as calculated, 16 years after his death. This was revolutionary, showing comets weren't random events but objects obeying Newton's laws of motion. Halley's comet has been observed for over 2,000 years, appearing in historical records from ancient China, Babylon, and Europe. It last visited in 1986 and will return in 2061. Unlike Halley's predictable orbit, 3I/Atlas passes through just once, making its brief appearance all the more precious. When we observe 3I/Atlas, we're using the same techniques astronomers have refined over centuries. Telescopes collect light. Spectrographs split that light into its component colors, revealing chemical signatures. Photometry measures brightness over time. Astrometry tracks position with precision. These methods, developed to study planets and local comets, work equally well on interstellar visitors. The laws of physics and chemistry are universal, so light from an object born around another star carries information we can decode with the same tools we use for local objects. This universality is profound. The universe speaks one language, and we've learned to read it, translating photons into knowledge about places we can never visit. Comets occasionally break apart under stress. 2I/Borisov, the previous interstellar visitor, showed signs of fragmentation during its 2020 perihelion passage. Pieces broke off the main nucleus, likely due to thermal stress as warming caused the interior to expand unevenly, cracking the structure. This fragmentation is common. Comet Shoemaker-Levy 9 famously broke into pieces before colliding with Jupiter in 1994. So far, observations of 3I/Atlas haven't shown clear evidence of breakup, though the multiple jets and complex tail structure might indicate fracturing or uneven surface activity. If it did fragment, the pieces would continue traveling together for a while before gradually separating. We might be watching one of the last intact configurations of this ancient object. The brightness of a comet as seen from Earth depends on multiple factors working together. Distance from the Sun affects how much it heats up and releases material. Distance from Earth determines how bright it appears to us. The size and reflectivity of the nucleus matters. The amount of dust in the coma affects visibility. Even the angle at which we view the comet influences what we see. For 3I/Atlas, predictions suggested it would reach magnitude 11 or 12 at best, faint but visible through modest telescopes. The actual brightness exceeded expectations during some periods, making the comet more accessible to amateur observers than initially anticipated. Comets often defy predictions, reminding us that nature retains its capacity to surprise. The naming conventions for comets follow specific rules. The letter C indicates a non-periodic comet, one not expected to return within 200 years. The year of discovery comes next, 2025 for 3I/Atlas. The letter N represents the half-month period of discovery, in this case, the first half of July. The number after the letter indicates it was the first comet discovered in that period. Atlas identifies the discovering survey. The interstellar designation 3I comes afterward, marking it as the third interstellar object. So the full name, C/2025 N1, Atlas or 3I/Atlas, tells us when and how it was discovered and its special status. These naming conventions help astronomers communicate clearly about the thousands of comets known. Pre-discovery images revealed 3I/Atlas was observable before July 1st. Astronomers searching archival data found images from mid-June showing the comet, already present but unrecognized. This is common. Survey telescopes take far more images than can be immediately analyzed. New software and human review often find objects in old data after their discovery elsewhere. These pre-discovery observations are valuable because they extend the baseline of observations, allowing more accurate trajectory calculations. For 3I/Atlas, finding images from June helped refine its orbital path and better constrain its origin. The past observations, overlooked initially, gained significance only after we understood what we were looking at. The physics of sublimation involves phase change without liquid. On Earth, ice typically melts to water before evaporating. But at the low pressures in space, ice can transform directly to vapor, skipping the liquid phase entirely. This process requires energy, absorbed from sunlight in a comet's case. As sublimation proceeds, it cools the surface, much like perspiration cools human skin. This cooling can create temperature differences across a comet's surface, affecting which areas sublimate most actively. The physics is straightforward, but the complex geometry of an irregular, rotating nucleus creates intricate patterns of activity. Jets, active regions, and seasonal variations emerge from these simple physical principles operating on complicated structures. The 3 confirmed interstellar objects show interesting age differences. Calculations suggest Oumuamua is relatively young, with a median age around 1 billion years, originating from the thin disk where young stars form. 2I/Borisov is intermediate, approximately 3.8 billion years old. 3I/Atlas appears oldest, with a median age near 9.6 billion years, originating from the thick disk population of ancient stars. This age diversity suggests interstellar objects are ejected throughout galactic history, not just from young systems. Old systems can eject material just as young ones do, through different mechanisms perhaps. These 3 visitors sample different eras of galactic evolution, each carrying information about planetary system dynamics at different times in the Milky Way's history. Telescopes on Earth must observe through the atmosphere, which absorbs and distorts light. Water vapor absorbs certain infrared wavelengths. Turbulent air creates the twinkling effect we see in stars, blurring fine details. This is why space telescopes like Hubble and Webb are so valuable. They observe from above the atmosphere, seeing clearly in wavelengths blocked from the ground and avoiding atmospheric distortion. For 3I/Atlas, space telescope observations provided the sharpest images of the coma structure. But space telescopes have limited observation time, shared among many projects. Ground-based observatories, despite atmospheric challenges, can dedicate more time to tracking a single object. Both approaches complement each other, each with strengths the other lacks. The future exploration of interstellar objects might involve prepared spacecraft waiting for targets. The Comet Interceptor mission plans to station a spacecraft at the Sun-Earth L2 Lagrange point, a gravitationally stable location about 1 million miles from Earth. It will wait there until a suitable target appears, either a pristine long-period comet or possibly an interstellar object. Once a target is identified, the spacecraft will maneuver to intercept it, studying it up close. This wait-and-respond strategy acknowledges we can't predict when interstellar visitors will arrive or what paths they'll take. By waiting in space, ready to deploy quickly, we maximize our chances of catching the next visitor before it escapes beyond reach. The cultural impact of discovering interstellar objects goes beyond science. These discoveries remind us that we're part of something larger. Our solar system isn't isolated, but exists within a dynamic galaxy full of similar systems. Objects from those distant places can reach us, carrying physical samples from alien worlds. While this doesn't mean we've encountered alien intelligence, it does mean we've touched, however remotely, the products of other star systems. In a universe where the nearest stars are light years away, where travel between systems seems impossibly difficult, these cosmic visitors bridge the gap. They connect us to the broader galaxy in a tangible way, small frozen ambassadors from the unknown. As we pass the halfway point in our journey through these facts, it's worth reflecting on what we've learned. 3. I/Atlas is an ancient comet, billions of years old, that wandered the galaxy since before our solar system existed. It happened to pass near our Sun, warming for the first time in perhaps millions of years. We noticed it, observed it with dozens of instruments, learned about its composition and trajectory. Soon it will leave, returning to the cold dark between stars, where it will travel for millions or billions more years, before perhaps, impossibly far in the future, encountering another star. We had a brief window, measured in months, to witness this encounter. The universe operates on timescales that dwarf human experience, yet in this moment, we connected with something ancient and far-traveled. Water detected in 3 I/Atlas connects this distant traveler to Earth. Water is common in the universe, formed wherever hydrogen and oxygen meet in cold environments. But its presence in an interstellar comet confirms that the chemistry supporting life, at least the water-based life we know, exists throughout the galaxy. The water molecules released from 3 I/Atlas formed billions of years ago, perhaps around a star that no longer exists, in a planetary system long since dispersed. Those same molecules now drift through our solar system, warmed by our Sunday water, is a cosmic connector, the same substance flowing through all life on Earth and floating through space in ancient comets. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. 3 I/Atlas orbits the galactic center just as our Sun does, each completing a circuit every few 100 million years. Planets orbit the Sunday moons, orbit planets. Electrons orbit atomic nuclei. Everything in the universe moves in cycles, patterns, endless repetitions, like your breath. Inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like comets silently tracing their paths through space, unhurried, unresisting, simply existing. We're almost there now, just a little further to drift. The galaxy is filled with orphaned objects, planets ejected during their system's chaotic youth, wandering alone through space, asteroids scattered by gravitational encounters, comets like 3 I/Atlas sent on journeys that never end. Current estimates suggest there might be more rogue planets drifting through the galaxy than stars themselves. For every star we see, there might be one or more planets floating in the dark, unbound to any Sunday. These orphans outnumber the attached worlds. The galaxy is not just stars and planets in neat systems, but a vast wilderness of solitary travelers, each with its own story of exile and wandering. When 3 I/Atlas eventually leaves our solar system entirely, perhaps in 2027 or 2028, it will become invisible to us. Its dimming light will fade below detection limits. It will continue existing, traveling, but beyond our ability to observe. This happens with every comet we discover. They enter our awareness briefly, teach us what they can, then slip back into obscurity. Only the rare periodic comets return for further study. For one-time visitors like 3 I/Atlas, we get one chance. What we learn now is all we'll ever learn from this specific object. Future interstellar visitors will each be different, unique individuals with their own properties. Darkness in space is not absence, but presence. The dark sky between stars isn't empty void, but space itself, physical and real, through which objects travel and forces propagate. 3. I/Atlas moves through this darkness, occasionally illuminated when it passes near a star, but spending most of its existence in the dark. There's something peaceful in imagining its journey. No sun to warm it, no planets to perturb it, no observers to watch. Just silent motion through the vast quiet of interstellar space, a tiny frozen world completing its slow orbit around the galactic center, part of the great rotation of matter that is the Milky Way. The scientific method requires skepticism and verification. When 3I/Atlas was discovered, multiple independent observers confirmed its existence and motion. Different teams calculated its trajectory using different methods, all reaching similar conclusions about its interstellar origin. This redundancy protects against errors. The discovery of an interstellar object is too important to accept without thorough confirmation. By the time it received its official designation, dozens of astronomers had contributed observations and analysis. This collective effort transforms individual observations into accepted knowledge. Photographing 3I/Atlas required patience and technique. The comet moves against background stars, so time-lapse images show stars as streaks while the comet remains fixed, or vice versa. Long exposures gather enough light to reveal faint details. Stacking multiple exposures brings out structure invisible in single images. Amateur astronomers worldwide shared their photographs, each adding to our understanding. In our connected age, a global community documents cosmic events in real time. Every clear night, someone somewhere was watching 3I/Atlas. The idea that we might someday travel to other star systems inspires imagination, but the distances are staggering. The nearest star system, Alpha Centauri, is about 4 light-years away. With current technology, reaching it would take tens of thousands of years. Even traveling at 1% the speed of light, an enormous achievement far beyond our current capability, the journey would take 400 years. Yet interstellar objects like 3I/Atlas travel between stars, naturally, taking millions of years perhaps, but eventually arriving. In a sense, these comets are doing what we dream of doing, crossing the gulfs between stars, carrying samples of their home systems to other places, their nature's starships. The composition of 3I/Atlas suggests it formed in a cold environment, far from its parent star. The presence of water, ice, carbon dioxide, and carbon monoxide indicates temperatures during formation were low enough to freeze these substances. These are volatiles, materials that sublimate easily when warmed. Rocky planets form closer to stars where temperatures are higher. Icy bodies form in the outer regions, beyond what's called the frost line, where temperatures allow ice to persist. 3I/Atlas likely formed in the outer regions of its home system, similar to where Kuiper Belt objects and Oort cloud comets form in our solar system. Despite crossing interstellar space, it retains clues about its birthplace. Light pressure from the sun is real and measurable. Photons, particles of light, carry momentum. When they strike an object and are absorbed or reflected, they transfer that momentum, creating a tiny push. For massive objects like planets, this force is negligible. But for small dust particles, light pressure can overcome other forces, pushing them away from the sunday. This is why dust tails always point away from the sun, regardless of the comet's motion. Solar sails, proposed for spacecraft propulsion, would use this light pressure to gradually accelerate, requiring no fuel. Nature already uses this principle in comets. The dust streaming from 3I/Atlas is gently pushed by starlight, an ancient force shaping the cosmos. Every comet is a time capsule. The ice and dust comprising a comet have been frozen since the comet's formation, preserving conditions from that era. Chemical analysis of comet material reveals the composition of the molecular cloud from which its parent star formed. Isotopic ratios, the relative abundance of different forms of the same element, provide information about temperature and chemical processes during formation. For 3I/Atlas, these measurements tell us about conditions in another stellar system billions of years ago. It's a form of archaeology, studying the past not through historical records, but through physical samples that have existed unchanged since ancient times. The trajectory of 3I/Atlas will carry it out of the solar system toward the constellation Telescopium. This is the direction it will be heading as it departs, though of course the stars in Telescopium are at vastly different distances and not related to each other. It's simply the direction as seen from Earth. Over the next millions of years, as 3I/Atlas travels through the galaxy, its path will curve under the Milky Way's gravitational field. It might eventually pass near other stars, though the galaxy is so vast that close encounters are rare. More likely, it will travel through interstellar space indefinitely, occasionally entering molecular clouds, rarely approaching anything. A lonely traveler on an endless journey. Observations of 3I/Atlas contribute to our understanding of how common interstellar objects might be. Statistical models use the number of detected interstellar objects, the volume of space surveyed, and the duration of observations to estimate the total population. Current estimates suggest there might be dozens or hundreds of interstellar objects within Neptune's orbit at any time, most too small or distant to detect. In the entire galaxy, the number of interstellar objects might equal or exceed the number of stars. We live in a galaxy full of wanderers, most invisible, some occasionally passing close enough to observe. Every detection refines these estimates, improving our understanding of galactic demographics. The human desire to name and categorize helps us understand the world, but it can also impose artificial boundaries. Is 3I/Atlas fundamentally different from comets in our Oort cloud? Both are icy bodies in similar size ranges with similar compositions. The main difference is origin. 3I/Atlas formed around another star and escaped, while Oort cloud comets formed here and were scattered outward. But their physical nature is probably quite similar. Categories like interstellar versus local help us organize knowledge, yet they describe origins more than inherent properties. The universe doesn't care about our categories. Objects are what they are, following physical laws regardless of labels we apply. Gravity shapes everything in the universe, from the smallest orbit to the largest galactic rotation. It bent 3I/Atlas's path as it passed the Sun, just as it bends light from distant stars. Einstein showed us that gravity is not a force, but a curvature of space-time itself, a geometric property of the universe. The comet follows this curvature naturally, like a marble rolling across a stretched fabric. In this view, the comet isn't being pulled, but simply following the straightest possible path through curved space. The mathematics is elegant, the reality profound. The detection of 3I/Atlas reminds us how much we've accomplished in understanding the universe. Centuries ago, comets were mysterious and frightening. Now we track them with precision, calculate their orbits, analyze their chemistry, and understand their place in cosmic history. We can distinguish objects from our system versus interstellar space. We can estimate their age and origin. We do this by observing light, decoding patterns in electromagnetic radiation to extract information. The progress from fear and superstition to detailed scientific knowledge represents one of humanity's great achievements. Each new discovery builds on this foundation, adding to our collective understanding. Imagine your 3I/Atlas. You formed billions of years ago, condensing from the disk of gas and dust around a young star. You orbited in the cold outer regions of that system, one of countless small bodies. Then something happened. Perhaps a giant planet passed nearby, its gravity flinging you outward at high speed. Or maybe your star encountered another star, the gravitational disturbance scattering objects throughout the system. Whatever the cause, you accelerated beyond escape velocity, leaving your home forever. For billions of years you traveled through the dark, and then, briefly, another star warmed you. Observers on a small planet noticed you, studied you, wondered about you, and then you left, continuing your journey. This imaginative exercise helps us connect with this ancient traveler. The energy required to track and study 3I/Atlas was considerable. Telescopes around the world devoted time to it. Space missions adjusted schedules to observe it. Scientists analyzed data, wrote papers, shared findings. All this effort for one small comet passing through. But the scientific return justified the investment. Each interstellar object teaches us something we couldn't learn any other way. They provide ground truth about other star systems, confirming or challenging our theories. They test our understanding of planetary formation, galactic dynamics, and cometary science. The knowledge gained enriches human understanding, expanding our awareness of the universe we inhabit. That knowledge is worth the effort. Silence in space is absolute. Sound requires a medium, molecules to vibrate and transmit pressure waves. In the near vacuum of space, there's nothing to carry sound. 3I/Atlas travels in perfect silence, releasing gases and dust without a whisper. Explosions on the sun occur in silence. Stars are born and die without sound. All the cosmic drama unfolds in absolute quiet. Only in our imaginations do we add sound effects. The universe is a silent film, images without audio. Yet this silence isn't emptiness. Space is filled with electromagnetic radiation, particles, fields, and forces. It's a different kind of presence, perceived not through ears, but through instruments that detect light, radio waves, magnetic fields. Silence doesn't mean absence. The perspective we gain from studying objects, like 3I/Atlas, is humbling. This comet is older than our world, traveled farther than we can comprehend, and will continue existing long after human civilization ends. It connects us to deep time and vast space, reminding us how small and temporary we are. Yet somehow, small and temporary as we are, we can observe this ancient traveler, decode its properties, and understand its story. Consciousness creates meaning. The universe doesn't care about 3I/Atlas, but we do. We assign significance through observation and understanding. That's a kind of power, perhaps the only kind that matters, the power to create meaning in an indifferent cosmos. Every observation has uncertainty. Measurements of 3I/Atlas's size, composition, and trajectory all include error bars, ranges of possible values rather than exact numbers. This isn't failure but honesty. Science quantifies uncertainty, acknowledging the limits of knowledge. As more observations accumulate, uncertainties narrow. Some questions gain clear answers. Others remain open, waiting for better instruments or new approaches. Living with uncertainty is part of the scientific process. We work with the best information available, update beliefs as new data arrives, and remain comfortable with unanswered questions. This intellectual flexibility allows science to progress, incorporating new knowledge without rigidity. The molecules released from 3I/Atlas disperse into space, eventually mixing with the interstellar medium. These molecules, which spent billions of years frozen in the comet, now join the thin gas between stars. Some might eventually be incorporated into a collapsing molecular cloud, becoming part of a new star system. In this way, material cycles through the galaxy, from stars to planetary systems to interstellar space, and back to stars again. Nothing is wasted. Everything transforms, recombines, continues. The carbon atoms in your body were once in stars, then perhaps in space, then in the solar system's formation, eventually in Earth, and now temporarily in you. After you, they'll continue their journey. We are all temporary forms of recycled stardust. As 3I/Atlas recedes, becoming fainter and more difficult to observe, we'll lose track of it. Telescopes have limits. Below a certain brightness, objects become undetectable. Eventually, likely sometime in 2026 or 2027, the last observation of 3I/Atlas will occur. Someone will image it, perhaps not realizing it's the final view anyone will have. Then it will be gone from human awareness, continuing to exist, but beyond our reach. This happens with every transient object. We observe until we can't anymore, then preserve the data and move on to other targets. But the object continues its existence, unconcerned with whether anyone watches. Reality persists independent of observation. The story of 3I/Atlas includes us. Its journey through the galaxy is independent of humanity, but the story we tell about it, the meaning we extract, includes human observers and instruments and analysis. We are characters in this story, the ones who noticed, who studied, who wondered. Our brief interaction with this ancient traveler is significant to us, if to nothing else. We create narratives to make sense of observations. These narratives are subjective interpretations, yet they're how we understand the world. The scientific facts about 3I/Atlas exist objectively. The story we weave from those facts is human creation, as much about us as about the comet. Looking up at the night sky knowing 3I/Atlas is out there, even if invisible to unaided eyes, changes the experience slightly. The sky isn't just backdrop but active space where things happen. Objects move through it. Events unfold. The universe operates on all scales simultaneously, from quantum fluctuations to galactic rotations. 3I/Atlas, invisible from any individual spot on Earth without aid, nonetheless exists, following its trajectory with perfect precision. Knowing this adds richness to the experience of standing under stars. The cosmos is more complex, more dynamic, more interesting than it appears to casual observation. Knowledge transforms perception, and so we reach the end of our catalogue of facts about this interstellar visitor. We've journeyed from its discovery in July 2025 through its properties, composition, and trajectory. We've explored what it tells us about the galaxy and our place within it. We've connected this small icy body to larger questions about life, time, and meaning. 3I/Atlas will continue its journey, indifferent to our attention. We'll watch until we can't anymore, then turn our telescopes to other targets. But for this brief window, we shared space with a traveler from deep time and distant space. That connection, however tenuous, matters. It expands our awareness and reminds us that we're part of something vast, ancient, and ongoing. The universe flows on, and we flow with it. Every moment of connection with the cosmos matters. 3I/Atlas passed through our solar system for a few months, visible for a season. In its billion-year journey, this was the briefest pause, a momentary illumination. For us, it was significant, a chance to touch something from beyond our home. These encounters remind us that borders we draw between here and there, between known and unknown, are permeable. The universe is not divided into separate boxes but flows together, connected by gravity and light and wandering travelers. We observed one such traveler. Perhaps somewhere, someday, another civilization will observe something from our system, a piece of Earth carried on solar winds to distant places. We're all part of the same cosmic story, written in starlight and dust. And so, our quiet journey through the story of 3I/Atlas comes to a gentle close. We've traveled from its discovery on a July night in Chile's desert to its closest approach to Mars and the Sun, discovering along the way that this ancient comet carries within its ice a record of the early galaxy, from the frozen darkness between stars to the warmth of our Sun's light, from silence spanning billions of years to the brief attention of human observers. We've glimpsed how interstellar travelers are both impossibly distant and surprisingly near. 3I/Atlas reminds us that the galaxy is not empty space between stars, but a web of connections. Much of the universe's activity happens in silence, in darkness, in places no one observes. These ancient wanderers teach us patience and perspective. Without such visitors, we would never touch matter from other star systems. By pausing to notice, we glimpse the extraordinary in what seems ordinary darkness. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity of every atom, every event, every moment in the universe. You are not separate. You are a link in the endless chain. Think about the unity of every atom in space, where all boundaries dissolve. Light, matter, time, all becoming one. You too can dissolve into sleep like that. No boundaries left between you and rest. Let your entire being dissolve into the gentle darkness, into the soft gravity pulling you into sleep. Prepare for deep sleep. No boundaries left, only peace. If this gentle journey through the cosmos brought you peace tonight, perhaps share it softly with someone else searching for stillness under the stars. One quiet share, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of distant comets to fade now, like morning mist dissolved by sunlight, leaving only the peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if Earth's gravity is gently pulling you down into your bed, into comfort, into rest. If sleep comes, let it carry you like a comet drifting through space, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, 3I/Atlas will still be traveling. Stars will still be burning. The galaxy will still be turning. But tonight belongs to stillness. Rest well, fellow traveler. And remember, you are made of stardust, connected to everything that ever was or will be. Good night.